Hello students, and welcome again to the Virtual Science 10 classroom. Today we're going to talk about the main 6 types of chemical reactions. Like previous lessons, there is a note page note pages that go along with this lesson that you are more than welcome to follow along with. So with chemistry, we find that things behave in certain ways depending on what is there to react with in the first place. And we can use this knowledge to eventually predict products. If we put this and this together, what most likely is going to be formed, as in predict our products. So it's important to know what the main types of reactions are so that we can look at what the reactants are and figure out the products. So one of the first types of reactions is the one that you're probably most inherently comfortable with, and that's called a synthesis reaction. It's when you take one thing, add it with another thing, and they join to combine one new thing. So you have one element or compound react with another element or compound, and it produces one product, one substance. So what you look for is you look for only one thing on the right-hand side of the arrow. An analogy that I use for this is kind of like your marriage. So you have one person meets another person, they fall in love, and they get married. So that is our marriage, where we have a happy couple at the end. All right, so we look for the happy couple. All right. The next type of reaction is, actually, you know what, I'm going to do the examples first. So here we go. We have one sodium reacting with one oxygen molecule to produce sodium oxide. Do you see how there is only one product? Now, technically there's two of them because there's a coefficient of 2, but there's only one type of product. There's no plus something else here. There's only one thing written on this side. There's no plus anything else. So this is an example of a synthesis reaction. So now going to our second type is decomposition. This is the exact opposite of synthesis. You have one reactant, just one thing to the left of the arrow, and it breaks apart into 2 or more things. Okay. An analogy for this is that happy couple is no longer happy, and they get divorced. Okay, so this is the divorcee reaction type, and the other was the marriage reaction type. Okay, so here what we look for in order to recognize a decomposition reaction, we look for one reactant. So here's my example, it's the exact opposite. We have one reactant, and it's breaking into 2 or more things. Now, technically, again, yes, there is a 2 there, meaning that there's 2 of that particular type of molecule, but there's not something plus something going to something else. There's only one thing. There's no plus sign on the left-hand side of this equation. So therefore, this is a decomposition reaction. Okay. So single replacement, that's when you have a happy couple. Oops, I don't know why it does that to me. It's really annoying. It's when you have a happy couple and then someone cuts in. So cutting in and dancing doesn't really happen anymore these days. It was a big, someone cut in on a dance back in the day, there would be some tea spilled the next day on the gossiping, but it's the idea that you have a compound and an element, and this element will come in and replace the metal in that compound. So that B gets kicked out of the relationship of that happy couple, and A takes its place. So the A and the B switch places. Actually, maybe I'll color code this a little bit differently. I'll put A in a different. Okay. So that's if the A was a metal. Okay. You can also have it where it's something else, where A is a non-metal. So it will not replace the metal in the reaction, it will replace the non-metal. So if it's a non-metal, it will kick out the non-metal in the compound. So that means C in this case gets kicked out, and it'll be B and A together in a compound. So this is if A is a non-metal. Now my analogy for this is a little bit risque and probably will get me in a little bit of trouble, but I call this the homewrecker reaction, because you have the single element coming in and breaking up that compound to form a new compound, and then another lone single element is formed. So an example of that is if you have a couple and they get broken up, and so there's a new couple. Oops. And I guess I should have like differentiated one of these stick man from my other stick mans. There we go. My stick man drawings are a little bit questionable. Another example. Okay, so it depends on where that, what type of element is reacting with the compound and which one gets replaced. And it's only a single element that is getting replaced, which is why it's called single replacement. So here we have chlorine. If you look up chlorine, chlorine is a non-metal. So we have lithium iodide here, but the lithium is a metal. It's the iodine, which is on the right-hand side, that little staircase on the periodic table of elements. So these two end up switching places. So the chlorine is now in, and the iodine is now, I should have done a different color for that one. The chlorine is now in, and the iodine is now out. It was a single replacement. Notice how there's only one arrow, and there's only one direction of that arrow. And that means it is single replacement. Okay. The next type of reaction is double replacement. So double replacement requires two compounds. Oh, and sorry, to go back to single replacement, what you look for is an element reacting with a compound to produce another element and another compound. For double replacement, you're looking for two compounds reacting with each other. So if I have A, B, it's a compound, two different things there, reacting with CD, which is another compound, made up of two different types of atoms. The metals are going to switch places, okay? Or you can look at it as the nonmetals switch places. Regardless, you're going to have A be with D and C be with B. Now remember, just because this one is the second one written doesn't mean C gets written second. It is not BC, it's CB, because C is the metal and we always write the metals first. But you notice how they completely switched places. So this is like changing dance partners. If you're doing a two-person dance, maybe a do-si-do partners, and the music says to change partners, you swap with another person and they take your old part, and the person that your new partner was with goes with who you used to be with. So here is an example of double replacement. We have ammonium reacting with sulfate and strontium with hydroxide. And you can either look at it as the metal switching places or the other way, the non-metal switching places. They result in the same thing, that your strontium switched places, so it's now with sulfate, green, and your ammonium is now with the hydroxide, which was pink. Okay, so they completely switch places. So this is a double replacement. Okay. Going back to single replacement, I forgot to show what the other one looked like. I just realized that now. But taking a little step back and going back to single replacement, we have magnesium, which is a metal, and it's going to take the place of hydrogen, which can be a metal or a non-metal, but because it's with chlorine, it acts as a metal in this case because it's the first one written. So these change place, which is why the hydrogen ends up by itself and the magnesium is now in the compound. All right. Now I'm going to actually skip combustion and go to neutralization. Neutralization is a form of double replacement. It is a double replacement reaction, but it's special. And the reason why it's special is it's because the compounds that are the reactants are an acid and a base. Now, we don't have time to go into acid and base science, but you can recognize an acid because it is an H. It is an H with a non-metal. Okay, so an example of acids would be HCl, H2SO4, HBr. So you see how there's an H on the left-hand side and there's a non-metal on the right-hand side. There is one exception, and that's CH3COOH. The H is actually, looks like a base. It's a really crazy one. It's acetic acid. It's found in vinegar. The H is actually on the end, and we just write it on the end for a reason, but trust me when I say that it is an acid because it is the H that breaks off. So what makes an acid is that when the compound goes into water, a hydrogen ion will break off, and that H plus floating around is what makes things acidic. Now a base is a metal with a hydroxide ion. So this is a metal. So an example of our metals would be things like NaOH, MgOH2. Okay. The exception is you'll see CH3COOH, and it'll look like it ends with OH, but that's the weird one that is actually a metal. Now, what makes a base is that when it's dissolved in solution, the hydroxide ion will break off from the compound. So you have an H from your acids breaking off, you have an OH with your bases breaking off, and together, what does two hydrogens and an oxygen form? They form water. So when you have an acid and a base, it is a double replacement reaction, but it is a special one, and it involves special notifications. So the H and the OH will join to form water. And the metal and the non-metal, and remember we have to write the metal first, so it's the metal plus the non-metal will form a compound. So we have an acid plus a base produce water and a salt. So if you can recognize an acid and a base in our reactants, we know the products are going to be the salt produced by the metal and the non-metal and the acid and the base, and it's going to be water. I don't have an analogy for this one, unfortunately. Okay, so if we look at our reactions that I have over here, you don't have these, I'm just showing you an example. Here we have it looks like a compound with a compound forming a new compound, so you're going to want to call this double replacement, and you are not wrong. You can just be even more right by recognizing, ooh, that was fun, by recognizing that, hey, this has an H and this has an OH, and they joined to form water. And if you look at the metal and the non-metal, they join to form the salt. So this is a neutralization reaction. And you will go over more of this in more detail in Chem 11. The last one, the most explosive one, the one I used to be able to blow up gummy bears for, is called a combustion reaction. You're going to have some crazy looking carbohydrate, which is going to be some amount of C's reacting with some amount of H's and maybe potentially some oxygens. The oxygen is not always there. This is what a carbohydrate is. It's a carb, and it reacts with oxygen gas. And it produces carbon dioxide and water, always. So how we recognize a combustion reaction, it has this crazy carbohydrate thing that looks a little freakish, and we are automatically start going, how am I going to balance that? Reacting with oxygen to form carbon dioxide and water. Carbon dioxide and water are always the products. So we look for carbon dioxide and water as our products. This happens in cellular respiration. So that's how we get our energy. We take our carbohydrates, we break them down, it produces carbon dioxide and water. So if I look at my examples, here is my crazy carbohydrate reacting with a bunch of oxygens. Doesn't matter how many oxygens, it's a crazy carbohydrate reacting with oxygens, and it produces carbon dioxide. Again, doesn't matter how many, it's carbon dioxide and water. So this is our combustion reaction. Okay, and those are the 6 main reaction types. I hope you found that helpful. Please let me know if you have any questions. I hope you're all doing well.